Welcome back. We have been discussing digital representation of microstructures, and during our discussions over the last few lectures, we have covered the basics of 2-point spatial correlation or 2-point statistics. We also discussed a little bit about how we think of microstructures as graphs and how we can represent microstructures and extract information and featureize the microstructures by use of convolutional neural network. So what we will do today is kind of continue on the same path, but with a slightly different angle, with a slightly different lens, and we shall see how we can actually start generating synthetic microstructures. Now, synthetic microstructures can become actually quite useful if you want to increase your overall size of the data set of microstructures that you have got. But at the same time, when you are generating a synthetic microstructure, we have to take care that it is similar to some sort of a real microstructure. So we will look into the applications of synthetic microstructures later on. But then for today, let us go ahead and try and understand what exactly are synthetic microstructures and how do we actually start creating synthetic microstructures. So before we start, it is probably useful if we just do a very quick recap of what we have done in terms of the understanding of microstructure representation and feature extraction with convolutional neural network and put it in context of real experimental microstructures. So for example, over here, you can see two different figures, and both of these figures show you the microstructure of steel. And if you look very carefully, you will see that these two microstructures are different, but at the same time, they look identical. In other words, what happens is, if you look at distribution of different phases, distribution of grains and all, that distribution is same, but exactly where those grains are forming, the exact length of the grains, those things differ. In other words, you have a little bit of stochasticity in the microstructure. Now, if you think of the microstructures in the real world that you will get during experiments, what happens is, suppose we are making a material starting from the liquid state. How does the material actually form? You go through a process of nucleation and growth. Now, where exactly in the liquid would you have a nucleation? That is a stochastic event, and therefore that is something which introduces a little bit of randomness, a little bit of probabilistic nature in how the microstructure evolves through the process of nucleation and growth. Now, if you look over long distances, you will notice that the variations will average out and the microstructures can be reasonably well represented by using even some fairly simple average features like your what is the average size of the grain, what is the phase fraction in the microstructure on an average, and so on and so forth. So these things stay the same, but then the exact spatial correlations and location of the phases, that will change a little bit. So you have a little difference from if you look at things spatially. Now, when we do a microstructure reconstruction, we start out with a hypothesis, and our basic hypothesis, of course, is that microstructures will have a underlying stationary probability distribution. If we do not have this assumption of there being a probability distribution that describes the microstructure, you will not be able to recreate microstructures which are different yet similar. So the key objectives when we are doing a microstructure reconstruction are as follows. You want to use a Markov random field in order to generate this synthetic microstructures with very similar distribution of different phases or different features. You also want to ensure that you are able to color the microstructure using some sort of heat maps. Now that becomes quite useful. So for example, you have used, let us say, a backscattered electron mode while collecting the microstructure of a material, and you might see that some of the grains which have a higher average atomic number look bright, whereas some of the grains where the average atomic number is lower, it looks dark. So you will be having a grayscale image, you will be having some contrast in the microstructure, and what you want to do is you also want to capture the contrast. Now that contrast does not necessarily have to be the Z contrast. It does not necessarily have to be something which is related only to the atomic number. You could have contrast as a result of the surface topography as well, something that you can capture typically using the secondary electron images. But the basic idea is when you have this grayscale microstructure, we should be able to color them using heat maps in a way that is meaningful to us. And finally, we want to upscale the low resolution synthesized microstructure using super resolution model. There may be certain cases where the images that you have got are fairly small, or maybe you have captured an image and you just want to look at only one part of the microstructure, supposing it's a heterogeneous microstructure, okay, and then there's only one region of the microstructure that you are a little bit more interested in. And so it would be useful if you could super resolutionize and you can get a super resolution model of that region of interest. So these are the basic three objectives that we will look forward to in the rest of the discussion today. Now, just to recap very quickly what a Markovian process is. Basically, a Markov property is something we say is a memoryless property of a stochastic process. Essentially, what we are saying is the immediate next step is dependent on the current step and not on any of the previous steps. This is a system whose history is not very important to us. And then when we are talking about a Markov random field, basically we are talking about a field in 2 dimensions that is going to satisfy the Markov property. Why 2 dimensions? Because in most cases, when we are looking at microstructures, we are not working with 3D microstructures, we are working with 2D microstructures. And then last time we also discussed how this icing model can be modified if you use a Markov random field type of approach. So when you are actually doing the microstructure reconstruction, you will have to input a grayscale image. So think of that as a m by n pixels. Here, for the sake of simplicity, we are simply considering a square image, so it is n by n. Now, once you have the n by n image, essentially what we have is a matrix which looks something like this, and then the value which is stored in every individual image is given by xij, and this value basically represents the intensities of the pixels. Okay. So I and j, they are basically going to be integer numbers from 1 to n, and using the ij index, you are able to locate the exact pixel in this matrix, and then the value in that matrix is going to correspond to the intensities of that pixel. Now, basically, there is a specific range of values that can be taken by the pixel intensity. So if you are using a grayscale type of image, then you will be having a number of grayscale levels. So the value of the intensity, the value of xij, is going to range from anywhere between 0 to g minus 1, where g is the number of grayscale levels. So for instance, if you have a situation where the number of grayscale levels is 256, which is the case for an 8-bit image, remember 2 to the power 8 is 256, right? So when you have a grayscale level, total number of grayscale levels is 256, then the value of xij is going to range from 0 to 255. So this is basically how you are assigning the values to the different elements of the matrix. They are essentially going to be the pixel intensities. Now, after you read your input image in the form of a matrix, you have to start sampling from there. Essentially, your image itself is going to be pretty big, and therefore what we are going to do is we are going to sample a smaller neighborhood. So how do we sample a smaller neighborhood? For that, we need to find out the proper local region of the microstructure which can be extracted, and then the idea is once you extract the small local region of the microstructure, you will try and capture the spatial correlations, for example, your 2-point statistics. And once you have your spatial correlations, from these spatial correlations, you start getting your probability density functions. So the process that we are going to follow is we will define a patch, or you can call that a window, which is shown over here in this light blue color. And so here in this case, we have taken a window which is basically a 5 by 5 window. So 5 pixels across and 5 pixels downward direction. And then the idea is that this window is going to capture a local region around a central pixel. So this one in dark blue, this is the central pixel which around which we are defining the neighborhood by taking this windows. So once you have extracted this intensity values in the neighborhood, you basically consider this patch as a sample, and you will then go ahead and start collecting different samples from the microstructure or different patches from the microstructure. Once you have got the different samples, you will use them for doing the machine learning part of it. Now, the idea here is if you look at this matrix right now, we have not yet applied any patch, and therefore we don't have any samples. And then what we do is we start sampling, and the way we start sampling is we will simply take this patch and we will translate it across and downwards in our image. So here I have used this patch only once, and therefore now I have got a single sample. As I translate this patch once again, I now get a second sample. So this is corresponding to the second sample, this one is corresponding to the first sample when I had placed the patch over the left hand corner. Now what you also notice is we are moving by one pixel. So when we are talking about sampling, we need to define two things. So one is how big the patch is or how big the window is. So our window size in this case is 5 by 5. We are moving this window one pixel at a time, and this motion is basically what we are talking about in terms of stride. So our stride in this case is 1. So you will simply go ahead and translate this throughout your entire image, and then you have got a pretty large number of samples. Now in this example, we are taking a window size of 5, and we are saying that in our image, which is n cross n, the value of n is 100. So that means if we are looking at the translations, the number of translation I can have in each direction is basically 100 minus 5 plus 1. So this is going to give me 96. So I can make 96 translations over here. Remember, my initial location is taking up this 5 pixels, and then I'm moving from here. So that is basically what I'm meaning by a translation. So I can make 96 translations in one direction, and because this is a square matrix, this is a square image, I can also make 96 translation in the other direction. And therefore the total number of samples that I am getting from here is 96 times 96, which will come out to be 9216. Okay, so from this single image, by choosing a window size of 5 and a stride of 1, I am able to create 9216 total. So having extracted these different patches, one can then train your machine learning model using this type of samples. So this one thing to collect the samples from a given microstructure, but then it is another thing when you want to recreate the microstructure. Remember, what we had discussed was you can think of the microstructure in terms of the microstructure function, which is nothing but a probability distribution function. So what that means is, if you look at this entire process like a stochastic process, like basically a probabilistic process, you should be able to use the probability distribution functions differently each time you do a reconstruction, and end up with different microstructures which are different but at the same time similar. So this is really the idea underlying the microstructure reconstruction. So when we do a microstructure reconstruction, we start with an empty matrix or a null matrix. You can say that all the pixel intensities are 0, and when we reconstruct the microstructure, we will have to go ahead and assign the proper intensity values to every pixel. So the way we do it is we will go ahead and create what we call a seed. So this is a random seed. Essentially, this is a sample which I have chosen from a set of samples from the image that I am trying to reconstruct. Now you can actually pick the seed in two different manners. So you can choose it randomly from all of the samples, or if you already know that one particular patch is more representative of the microstructure than anything else, you can simply say that I am going to take a representative seed and I will start with the representative seed. But however you do it, you will need to actually start with a seed. And what this seed is going to do is, it is going to give you a initial value for reconstructing this microstructure in an iterative process. So how are we going to iterate? We are going to look at that pretty soon. So what we now do is, we have to essentially take this patch and we have to translate it all around. We have to take this seed and we have to translate this all around. And so what we do is, initially we will take an unknown pixel for whose value we have to assign. Now if I have taken an unknown pixel, I need to then create a neighborhood for this pixel. So I had my seed window, and close to my seed window I took a unknown image, and then I have created a neighborhood around this image. So now what do I do? What I basically do is, I take a difference in the value of the pixels. So when I say I am taking a difference, what am I doing? I am simply considering this particular neighborhood. Okay, so I took this particular neighborhood, and from there I am subtracting out the sample, the first sample, and I am simply taking a square. So just bear with me. Let us go over with this mathematical process, and then we will discuss why we are doing what we are doing. So the first thing we do is, we simply take a difference in the values of the intensity of the pixel, and we are going to square it. Next, we are going to apply a Gaussian filter. So why a Gaussian filter? There is a specific reason why we are choosing a Gaussian filter. When you think of a Gaussian filter, essentially you can think of it as something which is going to separate out the central part of the image with the edges of the image. So just like when you are talking about a Gaussian distribution, the Gaussian distribution looks like this. When you are applying a Gaussian filter, essentially what we are trying to do is, we are going to give more and more importance to the central part of the image, and then less and less importance as we move outward from the central part. So you can think of the Gaussian filter as something which simply ensures that we are giving a higher weightage to the central image, meaning a higher weightage to this particular image than the other images. So in that sense, you can think of this Gaussian filter as something which is like a soft mask. Okay, so it's a soft mask, and it is going to ensure that I give more priority to the central pixel, but it also ensures that the pixels at the edge still have, even if a small priority, it is still a finite priority, and it is not a zero priority. So in that sense, this is basically acting like a small mask. Now what we are trying to do by taking the difference is, we are simply trying to figure out how different this part is from our sample, and then what we do is, we will go ahead and take a sum of all of these differences multiplied by the Gaussian filter over all of the samples. So in that sense, what I'm doing is, I am simply creating a measure of how different the microstructure that is being reconstructed is from the initial microstructure. And then what I want to do is, I simply want to minimize this thing which we call the distance measure. So distance measure I am defining as the summation of all the products of the Gaussian filter with the difference of the square of the difference values of the pixels. All right, and then essentially when I am trying to reconstruct the microstructure, I am trying to optimize the reconstruction process. I am going to minimize this distance measure. So in that sense, you can roughly think of it as not very different from your least square minimization type of thing. Okay, so that is essentially what we are doing when we are trying to do the microstructure reconstruct. All right. So with that done, what would be our next step? We will simply go ahead and translate this red window all around our microstructure. So as I am computing the distance, now I am starting to populate another set of data which has all of the distance values which is being measured. And when I do it once, I end up creating the central pixel for the microstructure that I am reconstructing. So what I'll be doing as I keep on translating this, I will keep on creating more and more points for this distance set, and I will be sampling more and more of the central pixels. So essentially what I will be doing after that is I will go ahead and start defining a threshold value for this distance. So I can come up with some sort of a rule that if the minimum value of distance is 0, I'll put the threshold as 10. So that way the minimum value does not go all the way to 0 and does not become completely black. Otherwise I can simply put a threshold of 1.5 times the minimum distance. So this is something that we can decide as we are trying to reconstruct the microstructure. And what this is going to do is it is going to force the intensity values of the pixel within a certain range. And then, as I said, you will simply go ahead and translate this neighborhood all around your initial seed, and you will go ahead and do it for the entire image that you are trying to reconstruct. So basically what you are doing is you are moving along the boundary of pixels which have known values based on the value of the seed, and then you are essentially shifting it one pixel at a time. So as you go through it for one turn, now one additional layer of pixel have what we call a so-called known value, and so you can again start moving outward, and you can again start going around in a loop around this known pixels, and that is how moving in a radially outward manner you end up recreating the microstructure. So if you look at the images, this will give you an idea as to how this type of reconstruction is working. So what we have done over here, in order to reconstruct the microstructure, we have used a random seed for the different runs. And so basically what that means is in each run we have selected the seed randomly, and therefore the initial window that we have selected, or the initial patch that we have selected, is a little bit different. But if your sampling is proper, each of these random seeds, even though they are different, they are still going to be quite similar. So you can see over here, this is the original microstructure, and then when I did the 3 runs, you will notice that I am getting images which are a little bit different. So for instance, here you can see that you have got a pretty large region of gray phase. Here a large region of gray phase is found over here. In this case you have a large gray phase region over here. So in other words, you are still capturing all of the features and you are finding common features appearing in each of the runs, but the placement of those features is a little bit different. But then when you look at it visually, it is very difficult to say that these are going to be completely different microstructures from completely different materials. So you can look at the original and you can look at each of these runs, and you can understand that these are essentially microstructures of materials which are fairly similar to each other. So this is how you have the stochasticity which is getting induced through a random selection of the seed. The second way what you can do is you can create a stochasticity by taking a random selection of pixel value from the distribution, but then you use the same seed. So if you look at how the image is getting created, you will see that the image is moving in a similar manner, but then the pixel value that we started with is a little bit different in all of these runs. So that is another way in which you can induce some sort of stochasticity in the microstructure. And remember, when we are trying to induce the stochasticity in the microstructure, we are also ensuring that even though those microstructures are actually different, they are still very similar to each other in terms of the probability distribution of the different key features. So statistically the microstructures are still the same, even though if you look at the individual pixels or the individual elements, they are going to be different. Now when you are doing the microstructure reconstruction, even though we showed it for a grayscale, there is no reason that you will restrict yourself to a grayscale. You can actually create a color map. If you are working with EBSD data, for example, having this color maps is going to be really useful. So you can reconstruct the microstructure in grayscale, you can reconstruct the microstructure in color map. It all depends on how you are setting up your Python script for doing this type of reconstructions. So microstructural reconstructions, they actually do have a lot of value. You might be thinking that if I already have a microstructure to begin with, then why do I really need to reconstruct it? As we go forward and as we move into the next lecture, you will see that there is a certain value associated with doing the microstructural reconstruction in terms of how do you perform a beginning to end machine learning model where the microstructure is important. Even apart from that, many times what happens is we end up with a data set which is very sparse, and you want to populate the data sets a little bit more, and therefore what you do is you make some sort of synthetic microstructures, and that's why you do the microstructure reconstruction starting with maybe different random seeds, and you end up with similar and yet different microstructures. And then of course if you have the properties associated with that, you can go ahead and start making this microstructure property type of machine learning models. So we are going to stop here for today. Thank you very much for joining. And as we move forward to the next lecture, we will be discussing more about how the processing structure and properties are correlated. And that is where you will really see the true power of the ability to do microstructure reconstructions. Thank you very much for joining.